Morning, everybody. I'm Roger O'Brien. I'm head of AMAP at the University of Sunderland, and I'm the technical and research lead on the Sustainable Advanced Manufacturing Project, which is an ERDF funded project. It's now in its second phase, so in total it's a £10.9 million ERDF project that will have lasted 5 years by the time we're through to completion. So the SAM project specifically focused at supporting manufacturing SMEs, ideally within the Northeast local enterprise partnership area, but we can support companies outside of that region if there isn't a similar equivalent scheme running in their local enterprise partnership region and they approach us. Project part funded by the ERDF and match funded by the University of Sunderland as well, and we get further match funding from industry. That's mainly through the grant projects that we run, and so far we've allocated we've allocated about £1 million worth, and we've got further £1 million worth of grants to support, which allows companies to invest in new technology or processes to start their product. But primarily as well, it's about delivering technical interventions around product and process with manufacturing SMEs. So we get involved in lots and lots of technical projects. We've worked with around about 150 to 200 SMEs so far in the project, which has been running about 2.5 years. So I'm not going to dwell on this next slide very long, and my presentation, you'll be pleased to hear, is relatively short, because the key crux of the presentation today is to tell you about the technologies around MultiJet fusion. But as I said, we're part of the University of Sunderland, and we just sit within that wider offer that the university offers. Within the SAM project, then we have effectively 4 streams of engagement, which is our technical support, where some of our technical team, the likes of Carl and other colleagues, can get involved in a technical project working with a manufacturing SME, and that can be a product or a process related intervention, and that can range in anything from 12 hours support up to a maximum of around about 15 days. That's fully funded, so it doesn't cost anything to the SME, and hopefully adds significant value and allows them to explore new technologies or new product developments. So we've done quite a lot of work with people who've been interested in additive manufacturing, many of who have come in to find out more about the printers that we've got, including the HP MultiJet fusion printer, and see how they can design and develop products for that and how it can impact their process. We can also offer support with research. These tend to be longer projects just due to the very nature of research, so these tend to be a little bit more collaborative, and we can allocate some of our academic researchers onto those, and again, they're fully funded, and they can have an extended duration. And before, when we said the projects are 12 to 15 days, that doesn't necessarily mean the 12 to 15 days of concurrent activity. That could be spread out over a period of time. As well as that, we have established a number, building on the capability of the factories that we already had and the equipment we already had at AMAP at the University of Sunderland. We've established a further 5 what we term micro factories, where we've invested in state-of-the-art equipment, some of it related to Industry 4, some of it related to augmented and virtual reality, some of it related to robotics and automation, and a large chunk of that money has also gone towards additive manufacturing as well. And that equipment is there for companies to come in, engage with, try before they buy if they want on that basis, and explore the technology so they can learn more about it to inform their investment decisions, or to see how it can support them in their projects and their business moving forward. And then, so that's all sits under the my area of responsibility in the technical research and development team. And then linking to this, we have grants. So we normally expect the SMEs to have engaged with us on a technical project, and then that allows them to access the grant stream of activity, and the SMEs can apply through a competitive process to bid for grants, which will be up to £50,000 worth of grant funding, but that's matched at certain levels. So I'll not go too much into the match, but it's around, depending on where you are, it's either a 25 or a 35% match. So if you had a £200,000 project and you were in Town and Wear, then you get £50,000 of grant funding towards that project. Again, not going to dwell on this one, but we've got a range of specialists sat within our team. As well as this, we draw upon the wider skills as well of our academic colleagues to support. But all of our technical development team are all industry based and industry focused. We're all from an industrial background. So we're very used to working with industry and working in industry and the time pressures that brings. So hopefully that your projects run along smoothly and to the timescales that you expect. Everybody in that team is 100% dedicated to the project, so they're there and available to work on the projects. Obviously, there may be a bit of a lead time getting to your project because there's quite a demand for projects and support, but we try and fit everybody in as quickly as possible. And just to show some of the areas that we cover, really, it's not all just about additive manufacturing, although that forms a large proportion of some of the projects that we've done. We can range from everything from electronics, maintenance, condition-based monitoring, process improvements. We do a lot of work in discrete event simulation and digital twin, looking at factory layouts and optimizing factory flows and factory planning. Augmented and virtual reality, obviously a lot of design work, design for manufacture, design for assembly, as well as the traditional CAD and CAM work that we would do as part of that design work. Quite a bit of metrology. We've got quite a lot of inspection equipment and reverse engineering. So we've had a number of people who've approached us to help them with either metrology requirements or indeed take a component, reverse engineer it, and then take it into a 3D printed process so they can create new fixtures or new parts or replica parts using our additive manufacturing. We've invested quite heavily in robotics and automation as well. So you'll see quite a range. That's not everything that we do, but it gives you a good flavour for the broad range of support that we can offer. So from a manufacturing SME point of view, in terms of how you can engage with our project, then via our website there is a registration form. We'll share the website a little bit later. You fill the registration form in, and that goes to our administration team, who do some eligibility checks to ensure that you're an eligible SME. That's then allocated to one of our team, who will hopefully be on this call a little bit later. And our business development manager would come out and have an initial review with you just to help start scoping the engagement. From that point of view, it then feeds into the team, and we allocate the project based on some discussions with yourself. And that can either, as we say, be either the technical team, a research project. It might be that you just want access to the factories, and from that engagement as well, and you can then look to progressing towards the grant process as well. So we try and do this, the turnaround from registration through to initial review and engagement with one of our engineers. We try and do that with him in 2 weeks. So it's a fairly quick turnaround. And then the project will be allocated. The team will start working with you, and as I say, it's a 12 to a 15-day engagement, but that could be spread over many months. We have some projects that have gone on 6 months, some a little bit longer, depending on what the customer particular needs and the intervention that we're doing with them. So that's really all I want to say today about the SAM project. There's some details on how to find us there. We're open to take any questions, although we'll try and do all the questions at the end. But you'll find us on LinkedIn, Twitter. Obviously, there's the Eventbrite page, which may have been registered through today. And our website is samprojectuos.co.uk. You'll find all the information about the project there, and including the expression of interest form to get involved with the project. So I'm going to hand back to Carl, and then we'll move on to the main crux of today's presentation around working with the additive manufacturing technology of HP MultiJet Fusion.
Sorry. Thanks, Roger. Give a good overview of the project. I'll hand over and introduce you to Maryam Qureshi now, who for her presentation looking at the HP MultiJet Fusion.
Great, thank you.
Oh, can I just say that there is a question box. If any questions come up during the presentation, just drop a question and then we can get to a Q&A at the end. Okay, thank you.
Great. Can you see my screen just before I start, Carl?
Yes, yeah, it's fine.
Perfect. Okay, all right, so I'll get started then. Okay, so thank you for joining this webinar. Thank you for having me. My name is Maryam Qureshi and I am a 3D print application engineer at HP. My role is to work specifically with HP's MultiJet Fusion technology. We've got a few different types of printers and working directly with customers to assess their current manufacturing limitations and to help find bespoke and cost-effective solutions to their problems. I help to implement the MultiJet Fusion solution into customers' businesses by encouraging them to use technology to innovate and design, and specifically by designing for additive manufacturing. So I feel like we kind of go hand in hand with what the SAM project is trying to do as well. Today, 3D printing has gone far beyond prototyping, reaching new levels of efficiency that enables every industry to viably create high quality parts at low to mid volume production. And it's become a technology that doesn't just empower the individual, it transforms organizations of all sizes and powers the future of digital manufacturing. So I'd like to take you through how our MultiJet Fusion technology works, the key advantages of it, and a real adoption journey. I'll show you how our technology can support your transformation from traditional manufacturing to a future of digital manufacturing, with insights from our customers throughout the way. So in terms of today's agenda, my mouse wants to move. There we go. I'll start off by doing a quick sort of introduction into HP and the 3D market and sort of why we're in this space. Then go into MJF basics, which is pretty much about the technology itself. I often think if you've not seen the printers, it's always useful to have a look to see what they look like, because they are different to what you're used to with traditional manufacturing. From there, we'll go on to why 3D. What's the big deal? Why are people now looking into this kind of technology? And then I'll show you an adoption journey and the sort of product life cycle throughout the adoption journey and where you can implement 3D throughout it. And then finally, we'll end up with new sort of paradigms, which is new design paradigms and trying to understand costing, because obviously 3D printing can be quite expensive, but there are ways for you to, if you understand the technology and how it works, there are ways for you to get the sort of best economical output from it. So the very first thing that I will start with is a video. This video, I always like to start my presentations with this video, especially when they're more around sort of design and helping people understand what the possibilities are with 3D. In the video, you'll see things that we are not able to do yet, but what it just shows you is the future and where HP envisioned 3D going.
To you, designers and engineers, captains of industry, and leaders of thought, anyone whose ambitions have ever exceeded what was possible. This is your moment, your rewrite history, the world is not flat moment. Every facet of how you design and manufacture is about to be reinvented, and it all starts here with the smallest of building blocks, the mighty HP voxel. You and it are about to change the world by advancing radical prototyping, accelerating manufacturing, and taking precision and strength to unheard of heights. From today forward, the 3D printer is a factory for thought, where the things we make will make us smarter, better, more human. What a future we'll create with new materials and embedded intelligence. Together, we'll bring extraordinary to the everyday and reality to dreams light years away. Welcome to the age of digital production, on demand, a world without waste, without inventory, without warehouses. Meet the first HP Jet Fusion 3D printers, the digital furnaces of the next industrial revolution. Join us as we engineer the never-before voxel by voxel. HP MultiJet Fusion. Keep reinventing.
Thank you. So yeah, so I always think it's very useful to start off with that, and then also explain a little bit about where HP are and our journey to 3D printing. So we officially launched our first printer back in 2016, which was the one that you saw in that video at the end. It's quite a large industrial machine, and at the point that we released the printer, we'd obviously been watching the market for a very long time, and we'd made the decision that, you know, the 3D printing world was brilliant, and you know, it's been around for 35 years, but predominantly 35 plus years now, but predominantly it's been mostly used for prototyping. And we knew that that prototyping space was a very, very small space in what was a larger world of manufacturing, and we wanted to try and hit that manufacturing $12 trillion business, and not so much the 3D printing market. We really wanted to release a disruptive technology that was going to be able to actually manufacture end use parts for people. And so when we had a look to sort of enter this industry, we realized that there was three things that we needed to unlock the market. So product capabilities, and we truly do believe we've got a superior product. Material price, I'll go into this later on, but you know, 3D printing is still a lot more expensive than injection molding when it comes to your final part piece cost. So material price was important, and material selection is what we found. And so we entered the market with an open materials platform, which meant that, you know, you couldn't just use any material within our machine, but it meant that anybody could sign up to become a material manufacturer for us. And that was kind of what we did. As we were a little bit naive as we entered the market, and we discovered actually you didn't just need something that was going to unlock the market, you actually needed something that was going to accelerate the adoption of it as well. And this is what we learned once we started working with potential customers, was that one of the things that was very limited was actual understanding of design for additive manufacturing. I mean, everybody knows, engineers know, you know, they're taught to design for injection molding, to design for CNC machining, fabrication, etc. But there's very limited knowledge about designing for additive, and then specifically designing for a specific technology, so the MultiJet fusion. So this was something that we internally realized ourselves, our engineers really lacked knowledge of how to design for additive manufacturing. We discovered that you need to be able to enable new supply chains. Again, internally for us as well, we wanted to start adopting this technology, but none of our suppliers had this technology. So even if we wanted to manufacture with it, it was very difficult to try and find the avenues to go to try and manufacture. Using our own technology. And then standards and policies, the more markets we enter, the more that we realize that, you know, when it comes to 3D printing, because it has predominantly been looked at a prototyping method, there was very limited testing out there for materials. There was very limited certifications that you could get. Even processes, it was difficult to, you know, there was processes for injection molding certifications, but not for 3D printing. And so standards and policies was something that we knew that we needed to help accelerate the market. So, you know, we really changed our own internal mindset, and this is kind of what we will go on to in the adoption journey when we get to that section today. But that was just a bit of an introduction into HP and sort of why we're in this space and what we think we can offer. So how do you choose your parts, and sort of why 3D printing? What's kind of the big deal about it now? Oh wait, hang on, sorry. I'm supposed to go MultiJet Fusion Basics first. That was an error. So MultiJet Fusion Basics. So in this section, you will understand how the technology itself works. Just, you know, a little bit of the, not a deep dive, I'm just going to give you a basic overview in 10 minutes. Understand the subsystems of the machine and how they interact with each other. And I'll explain this in more detail, but, you know, we've got a couple of different machines, and the larger machines they're not just a single printer, standalone printer, they've got other sections with them. And then we'll have a deep dive into the fusing science of the process and how it works and why we're able to get, you know, the superior mechanical properties that we talk about, especially in our Z orientation, sorry. You know, we get very, very good strength. So the technology itself, the best way of sort of describing it is this kind of in between a material jetting, which uses print heads, and a binder jetting process, which uses print heads and powder. We are a technology in our own right. We are classified as powder bed fusion. That's what we do. And by fusion, we do mean fusion. We're not just sort of sticking the parts together like you do, materials together like you do in a binder jetting process. We're actually fusing it. It's actually melting to its melting point and sticking together. So I'll go into that afterwards. But just to get rid of any kind of misconceptions, we are a separate technology called powder bed fusion. So how does it actually work? Well, the process itself is split into 7 stages, very similar probably to other 3D printing technologies that you're used to, where you've got like a 3D modeling stage, then you prepare your job within a 3D printing software, you send it to the printer. With our printer, there is, with our larger printer anyway, I'll get onto this afterwards, with our larger printer, there are 3 stages to the process where we actually do material loading within one of the machines to allow you to have traceability and mix your powders. We then have a separate machine that does the actual printing, and then you go back to that original machine for cooling and mixing the powder again. Then you have an unpack process and a cleaning process, and then if you wish, a secondary post-processing. Now, with the machine that's at Sunderland University, they've got the kind of smaller, more color printer that we have, and that is just one single machine that does all of these kind of 3 processes that you can see above over here. And in the next slide, you'll see the kind of software workflow and recommendations that we have. So I'm not entirely sure what software that you guys are using, but pretty much the process tends to be the same. You use whatever CAD or graphic design software that you use, and you convert your file into like an STL or a 3MF file, and that then can go into the software where they can play around with it to send it to print to the actual printer itself. And you know, there are different types of files that the printer can accept, and you know, this is something that Carl can go into with you in more detail afterwards. So the next slide is a video of the technology and how it works. And like I mentioned, it's a video that's not about the smaller printer, it's about the larger, more manufacturing related printer, but it's just to show you the process and you know, how it works and kind of why we think it's really able to help you manufacture if you get there at some point.
Introducing the HP Jet Fusion 5200 series, HP's most advanced plastics 3D printing solution. Made up of a printer, build unit, processing station, and HP's first natural cooling unit. Now you can unleash new growth and scale your production with an optimized workflow designed for production environments. The build unit is inserted into the printer to initiate printing. HP MultiJet fusion technology delivers dimensional accuracy and repeatability, allowing you to produce functional parts with best-in-class isotropy, while uniquely predictable and consistent print times for any type of part enable you to optimize production. When a build is complete, the build unit is inserted into the processing station and prepared for cooling. The HP Jet Fusion 5200 series natural cooling unit is designed to remove and cool each build naturally, thereby enabling continuous production. The natural cooling unit is placed on top of the build unit in the processing station. The slicing blade is removed and the material collector attached to aid extraction. The processing station's RFID sensors register the natural cooling unit and the identity of the build, prompting extraction to begin. During extraction, the internal platform of the build unit is raised, moving the build into the natural cooling unit. When the transfer is complete, the slicing blade is reinserted and the material collector detached. The natural cooling unit is then removed from the processing station using the HP recommended Hoffman forklift 5200. It is then stored and left to cool for 30 hours. Meanwhile, the empty build unit can be prepared for the next job, which starts with material loading. Fresh and reused material is automatically mixed according to the predefined mix ratio and loaded into the build unit in a clean, enclosed process. The build unit is then returned to the printer and production can continue. When a stored build has cooled completely, it is ready to be unpacked. The natural cooling unit is inserted into the processing station in the unpacking position. The lid is removed and the natural cooling unit cover put in place to ensure the material remains within the processing station for a safe unpacking process. During unpacking, the unfused material is extracted for reuse and the parts removed for post-processing. With unpacking complete, the natural cooling unit can be removed from the processing station to await the next build. The HP Jet Fusion 5200.
So that was a little bit about the technology itself, so you can actually see what it's like and how it works. I'm not going to delve into it too much. The one thing I will say is, as you saw within the video, there was at least 4 different parts to one printer. With the technology that's at Sunderland University, it is everything happens within the one printer. So your material mixing, your printing, the cooling of your parts, the recovery of your parts. Even in that machine, the recovery of the parts is actually automatic. So the powder is actually automatically taken out and you're left with a part covered in a small layer of powder that you can then either dust off and then take to a bead blast cabinet. So the concept is exactly the same. It's just all done in one machine rather than multiple machines. And the reason for why we've done it in multiple machines for the bigger one is purely for productivity, is that if you really are using the technology for manufacturing, you don't want to have to wait for your machine to have once the parts are built, you don't want to have to wait for the parts to cool down within your machine before you can recover them, because the cooling time can be quite long, and so you want your printer to be able to print 24/7. So for that reason, we've created it in this way, so that you can easily switch out a build and put a new one in, so you can continuously print. So in terms of the process itself, you saw in the video that there was sort of like a white powder and then something black that was added to it. So what we effectively have is a material which is in the form of a plastic or polymer powder at the moment. So for example, PA12, polyamide 12, we put a layer of that powder across the bed, and then to it we add agents. Now in the video you saw a black agent being added. There are 2 agents that we add in that technology, because that printer is not capable of printing in color. That one is just gives you sort of grayish blackish parts. So the agent that we add is a fusing agent, which is in this diagram is the black droplets, and that is applied where you want your part to actually be printed. and then we apply a detailing agent around the edges or where you don't want fusion to occur, which helps reduce the temperature and stops absorption of the infrared light that we then pass across the top. So the area that's got the darker agent, the fusing agent, absorbs that energy and melts to the melting point of the material. So in this case, it's about 182 to 185 degrees. And the area that's got the detailing agent remains as powder. And then we repeat that process until you have your part. Now, in the color machine, the difference is that we still have the fusing agent on the inside, but on the external side, we also have a bright fusing agent to which we add color, which is the sort of the full CMYK, or we add the sort of white coloring or no coloring. And so you have the capability of producing white or color parts, and then we add a detailing agent right at the end. So there's an additional step in there that allows you to print in color or in white. So that's kind of the process and how it actually works. In terms of the mechanical properties of it and what's actually happening, the reason for why we do say that we've got isotropic parts is because of the fusion that's happening in our Z axis. So just like any process is an additive manufacturing process, and so we are adding layers of powder, but the difference is that as we're adding those layers of powder, we're melting or we're heating the powder to its melting point. And so what ends up happening is wrong way. What ends up happening is that in between the layers, we end up having molecular diffusion and reaction entanglement, which allows the layers to actually fuse between themselves, giving you a much stronger part. Rather than one layer sitting on top of another layer, those layers are now actually entangled within each other. The crystalline chains are actually crossing over between those layer boundaries, producing a truly sort of stronger part, which is near enough equivalent to an injection molded part in terms of strength. So that's kind of the way that it actually works. And then this is the Jet Fusion 500 series, 300 500 series. I believe AMAP's got the 500 series, so it's the slightly bigger one, and it allows you to print in. Do you guys have full color or is it just white? Sorry, Carl, I don't know if you're there.
Yeah, I'm here. Sorry, to turn the microphone back on. Ours is just the white one.
Just the white, yeah. So you're able to print in the white color. So the parts that you produce will look like in this model, this sort of area over here, that's the whitish area. So there'll be full white parts. Yeah. But still without that great strength that we have within our parts. And then, like I said, everything, the entire process happens in this little small machine, which is a very complex machine for something so small. And that is the full kind of workflow and how the technology itself works. So now we will go on to how to choose your part and why 3D. Apologies about the mistake earlier with my slide. So in this section, hopefully we'll understand the main reasons to adopt 3D printing and particular MultiJet Fusion. What are the key value propositions for it? Learn how to identify the best applications for MultiJet Fusion within your business, because not every application is the correct application. So hopefully we can show you where to kind of identify those opportunities and how to identify those opportunities, and then understand the why 3D printing behind some real applications. So I'll kind of divulge into those key value propositions and show you some examples from each of them. So why are we here today? What we're finding is that market and consumer trends are showing that companies are looking for faster development cycles. They want quicker time to market, and a lot of companies are now moving towards mass customization. We've got companies like Coca-Cola who are putting people's names on bottles, Nutella who are putting people's names on bottles. What's the reason for it? It's because people like to see things that are slightly bespoke or slightly customized. So that's kind of the reason for why a lot of companies are now moving towards mass customization. You've got a high level management in companies that are now starting to look for double-digit operational improvements. So most options are most things that they look at, and it might only have a small amount of savings, let's say 5% savings or something, and these don't look as attractive as what you're seeing with 3D now. In a lot of cases, you can see significant weight reduction if you're going from CNC parts to plastic parts, up to 80% in cases or more. You can have savings in costs as well, and again, I'll show you some examples of these. So it's starting to look like a real positive contender when it comes to looking for large operational changes. And then also what we're finding is that, like I mentioned before, is changing mindsets to designing for additive manufacturing is one of the biggest factors, because what we're finding is that without this, nothing is going to move forward. If you're just looking to replace your current part like for like to a 3D part, it's very unlikely that you're going to see much value prop from it. So, if you're used to designing for injection molding or machining, you need to start thinking about now designing for additive. And just like, with injection molding and CNC, you've got your own guide, comes with its own guidelines. And CNC is actually the total opposite of additive. It is subtractive technology. So the same thing is you need to start thinking about 3D printing with a new mindset. You need to understand how the technology works and how to design for it. Instead of thinking about draft angles, you might now be thinking about orientation within the build, that kind of thing. So just people need to get into that mindset, that change mindset. So why 3D, and specifically more why MultiJet fusion? So in general, why does it make a difference? As you can see, it's hard to change. As I mentioned, it's hard to change the mindset of engineers because they're used to doing things by designing for the way that they know how to design it. But adopting a new technology, you need to see what the advantages of it are. And so one of the advantages that you get with 3D printing is a time advantage. So you can have sort of faster development cycles. You can have new designs that are for short runs and series production. So it can allow you to get to market faster. You can have economic advantages. Majority of the time, if something doesn't have an economic advantage, most companies are not going to do it unless it's got a significant advantage to their workflow process. It needs to have an economic advantage. And so what we're finding is where you've got sort of low volume parts or newer sort of business models where, for example, you can have personalization, 3D print really makes makes sense from an economical point of view. Then you can also have performance increase. So you can have parts that are improving in their performance in comparison to what they would have done if they were injection molded or machined. And as well as, you can have one part that does multiple functions, whereas previously you might have had to have multiple parts do the same function. So you can have an increase in performance. Personalization, that's one I don't feel I need to explain when it comes to 3D printing, because literally every single thing that you build in a printer is individual and not a copy of sort of the thing that's sort of the tool that's making it. So you can have personalization just comes part and parcel with 3D printing. And then finally, sustainability. Sustainability is obviously a huge topic at the moment, and again with 3D printing we see it as a very sustainable technology. Not to mention, just to start off with, because of material price, you are trying to use as minimal material as possible. Firstly, the materials are also recyclable, and as well as that, we do have a material within the larger machine that is made from renewable sources. And finally, the end goal is for 3D printing is that you are printing on demand, so you're only printing what you need. So, gone are the days that we hope where people will have piles and piles of inventory within a warehouse, which majority of the time, let's be honest, half of it gets chucked away and is unused. And so, you would only be printing on demand when you actually need that. So it is a highly sustainable technology. Not just ours, but 3D in general. So why 3D, how to use it, and how to pick kind of the best applications for yourself within your company. So using those 4 main drivers, let's leave sustainability out of it for now. Using the 4 main drivers, you can create a checklist that can be applied to your parts that you're considering converting to 3D. So the more ticks the part has, the higher the value of the application. So for example, if it was a time advantage and you knew that if one particular part was going to have a time advantage, but also have an economic advantage, a performance increase, and personalization, 100% that would be a brilliant case for you to go to 3D printing. If it was just going to have one of the increases, one of the if moving to 3D printing is only going to improve it in one way, then it might not have such a strong business case. But like I said, you know, if it's a time advantage and it's going to let you go to market faster, then yes, it might be worth you doing it. Or if it's personalization, for example, which we're finding in the medical industry at the moment, that can have a huge advantage just on its own, whether it costs more to produce or not. Majority of the time it doesn't, but whether it costs more to produce or not, having something that fits better, especially in the prosthetics and orthotics industry, is a huge advantage. So, you know, it just this kind of slide, and I think you've got it in the handouts as well, will just help you identify kind of which applications to focus on. So what I wanted to do now was show you an example from each of these different value props, so you can see, you know, where people have used 3D printing and the reason for why they've used it. So the very first one is time, and the example that I'm using here is actually a HP example. It's an internal example. It's from when we were in the process of producing the 300 500 series printer. So this is the one that's at the university. When we were producing this printer, we had announced it, I think, a good year before it was actually available in the market. And because, you know, we'd created the first kind of prototype of it, we knew where we were going with it. But when it came to producing the final sort of design, we discovered very close to the end date of the launch of this printer that actually we wanted to change the way that the powder was sort of set around the printer, and we needed 2 new subsystems. I think one was a humidification system that we didn't have and we hadn't created, and we had very limited time to create it. So what we decided to do was produce this in multiple different materials. So had we not had 3D printing at our fingertips, this design that you see on the left hand side would have taken us around 13 to 26 weeks in total to complete. But because we mixed traditional manufacturing, so you can see there's a bit of sheet metal in there, and 3D printing, we were able to get to the new subsystems within, I think it was 2 to 4 weeks, and that significantly helped us with our deadlines, because if we'd had a delay of 13 to 26 weeks, it would not have looked good for you know, for our own sort of stakeholders and shareholders and people that we have to respond to. So for us, it made it was a huge advantage to be able to use 3D printing and get that time saving that we really needed. And all the complex parts, you know, became 3D printed, and all the easy parts remained as traditional manufacturing methods. So, you know, it was a bit of a combination of technologies. The next one I wanted to show you was this as an economical advantage. Now, though I'm showing you this example as an economical advantage, it's got many other advantages. So this is also a HP example within our manufacturing lines. So this is a drill extraction shoe. And within our manufacturing lines, as you know, HP, as well as 3D printing, we work in the 2D world, and we produce millions of print heads. So the nozzles of the print heads that we use are manufactured by a laser cutting process, and the process requires water to avoid overheating, and overheating in the laser, and then there's also like some silicon plates. So the drill extraction shoe is used during the cutting process in order to remove the silicon sludge and water that continuously is produced and appears. And the shoe creates a more efficient laser drilling process due to the requirement of silicon debris being freed from the printhead production. So this drill extraction shoe was originally a part that was machined, and it was actually stainless steel. And you can see on this side over here that it was made up of 7 separate parts, as well as a load of sort of bolts and things. And what we basically did was, what we found was that they were having to be replaced every sort of 6 months. You know, the sludge and everything would get kind of stuck inside of the shoe, and it was very difficult to clean it out. So every single time we wanted to order one, we'd have to place an order for, I think it was 6. That was sort of the minimum order quantity. And so this part as well also cost $450 to just single one was $450 to produce. So we thought, okay, first of all, we don't need it in stainless. So the first thing we did was change it to aluminium, because stainless is great if it's going to last a long time, but if we're replacing every 6 months, what's the point? So we produced an aluminium version. So that $450 version over there that you see is aluminium. And then we thought, you know what, let's have a look at using 3D printing instead. So we ended up with a design that you can see on the right hand side over here, which is a single part, so it no longer has 7 parts. It still does have a few bolts to put it into place. These pipes over here that were previously 2 pipes that were bent are now designed properly and optimally for the flow that comes through them, so that they don't have build up, and so they function better. And as well as that, the entire design is much lighter as well. So it actually had I think an overall weight reduction of 90% from the aluminium version to the plastic version. But the biggest advantage here was the cost advantage to us. This one was costing us $450. This is costing us $18. So significant economic advantage. And this is just one of the many examples that we've got of parts that are within our manufacturing lines. We, you know, one of our centres, manufacturing centres, has purchased a machine purely off the back of this, because they found savings in so many different manufacturing line tools and manufacturing line aids, that they were able to justify purchase of a machine. So that's a really great example of economic, as well as, like I said, design improvement, performance improvement, weight reduction, etc. And even delivery time. You know, the machined part would take 3 to 5 days to arrive. This one only takes a little less than 24 hours. If you printed that in house, you'd have it very, very quickly. So, you know, loads of advantages all around with this one. This example here is for the performance increase. So this is a customer of ours in Spain. They're a small company, and they're called FISEP S3, and they produce different things, but this particular component that they were producing was a paint arm to paint construction beams. And so I'll let the guy explain it in the video, but he found a performance increase by changing to 3D printing, and specifically MJF.
FISEP S3 belongs to FISEP Group, which is a multinational company that constructs machinery for structural steel. So when you see a building or a bridge, all the metal structure was probably made with one of our machines in over 30 countries all over the world. We never considered using 3D printing for production until we saw HP's MultiJet fuse in action. Now we're doing parts which we weren't able to make before. Now we do them in-house, and we have them the next day. The machine that we're building is a paint machine for industrial steel. Once we saw how the parts come out, we noticed how strong and light they were, then we just redesigned the entire machine based on this technology. 40% of the machine is done in 3D now. The robotic arm, which holds the paint nozzles. In a traditional machine, this arm is about 1.5 meters high. We were able to reduce it in 3D to 300 millimeters. You can't design it any better than what it is now. And making the part so small, we were able to save a lot of space, where we were able to add other systems without increasing the floor space that the machine takes up. Just making one part in 3D can help you rethink the entire machine. What HP has done is made us a machine that can not only do the prototypes for us, but also do the final production. This is where it excels, because now we don't have to wait 12 hours to make one part. In 12 hours, we can make 100 parts.
So just going back to that, one of the things that he mentioned was that they was able to have performance improvements. So, you know, making it lighter, smaller, etc. What they were also able to do, because they made it lighter, was add webcams. And they added webcams onto the paint arm so they could see how the paint was being sprayed. And they found that they had a lot of wastage of paint because of the angles and things. So they were able to, by applying webcams, then actually improve the way that the arm itself sprayed paint onto the beams, which saved them money, additional savings in other places. And then the final example for this section is personalization. So with personalization, like I said, the industry that's really benefited from this the most, from what we can see anyway, is the orthotics and prosthetics industry, medical industry, anything that's obviously to do with people and personalization. And the example that I've got here is for a company called Invent Medical, and their story is quite incredible. They were a small business in Czech, and they saw one of our early announcements of our printer. I think it was back in 2016, and they were like thinking, you know, this is a great technology. Actually, we think we can really use it for what it is that they wanted to do in terms of personalized prosthetics. So they tried to reach out to us, and you know, it was very difficult to get hold of HP, and they were unable to reach us. They created a website which was dedicated directly to trying to get our attention. They started sending us blasts on Twitter and social media to try and get our attention, and eventually they managed to get our attention. This was prior to us actually properly launching the printer, so we ended up working with them in terms of sort of development and the early stages of the printer and sampling and things like that. And they're kind of way ahead of the ball game now when it comes to 3D printing, in terms of the rest of the industry as well. The designs that they come out with are so different, and so original and innovative in comparison to a lot of the other designs that you're seeing. So this example that you can see here is a cranial remolding orthosis, and what it basically does is when a child is born with a head, either perhaps like a hole in their head, in their skull, or if their skull needs sort of reshaping, you can wear this to kind of remold the head. Now, previously, this would have been made out. It was slightly heavier. It was made out of multiple different materials. It was quite complex. It would have to be adjusted as the child got older and bigger. What this current design does is the internal side of it is like a mesh type structure, which is actually flexible. Even though it's printed in the PA12 material, it's flexible purely by design. And then it's got another layer inside of it, and then it's got the external layer, which is hard to protect the child. So it's soft on the inside. It's got another sort of mid layer inside in the middle of it, to provide like a little bit of extra cushioning. And then it's got the hard outside that, you know, you don't want anywhere near the child's actual head, but then will protect it from hitting their head anywhere. And so this is all printed now. It's printed in 2 pieces purely for economics, but it could be printed in 1 if they really wanted it to. And it's printed in 2 pieces. It can be adjusted as the child grows older, and there's no complexity of the way that they used to manufacture it before in a warehouse with multiple different materials. So they've seen a huge advantage, not just on this, but many other applications that they're producing. What they've done is, their story is absolutely brilliant. So personalization is sort of part and parcel with 3D printing. So moving on to kind of just before we move into the next section, I just wanted to show you this graph, which is a graph of sort of a product's life cycle, and on the left hand side you've got volume of parts, so you can see that as the part moves down the process, let's say, more parts are produced. So in the most of the parts are produced in the production section, And what you'll find with kind of 3D is that the graph looks like the inverse of this, the total opposite. You'll find that 3D is used a lot at the start in the design stages, little to never in the production stages, and then some places are using it for the long tail spare parts end. And so what I'm going to show you in the next section is the adoption journey of a company, and that specific company is HP, and how we adopted 3D printing throughout our company and different areas of the product's life cycle. Hopefully maybe you'll get some learnings from it. So in this section, hopefully by the end of it, you'll understand how HP adopted additive manufacturing in different products across different stages of the PLC. We had to put numbers to the reasons of adoption, again explained in sort of previous areas, and get familiar with different examples that can start to ignite application sparks within your own organization and hopefully give you ideas. So just looking at that graph again, like I said, in the X you've got the well, I didn't say this, but in the X you've got the time along the product's life cycle. So obviously from its development all the way to its aftermarket service stage, and then in the Y you've got the production volume. And so the graph for the 3D tends to look like the total inverse. So what we found within HP was that the very first area that you can look to adopt the technology, if you're not already doing so, is prototyping. Now for us, we had already adopted 3D printing within prototyping, and prior to the release of our own technologies, we were using competitor technologies to produce 3D printed prototypes. So for us, this was not an area where we're going to show our adoption journey. We were already doing this. In fact, some of the earlier HP printers, sort of the very first few, did have parts that were made by other manufacturers within them, because we didn't have our own technology at that point to produce parts with. And now we use our technology because we've well, not for everything, but the things that we think it's useful for, we'll use it for that. And it's not one shoe fits all. You can't use 3D everywhere. There's specific areas where you can use it, and specific areas where you can use HP's technology. So prototyping is one area we were already using it, but a place that we weren't really using it was using it for molding. So still during the prototyping stages, yes, you can produce your actual prototypes with 3D printing, but you can also use 3D printing technology to produce molds and to produce aids, I guess, that can help you with the the initial production run. So we weren't using it for things like reaction injection molding or blow molding, and this was a place where we realized actually we can start to implement the technology. When it comes to short runs, 3D printing is great to produce the actual mold itself. So this is just sort of some of the areas, and metal sand casting as well for the green part, silicon molds, thermoforming molds, and then also machining MJF parts. So these are other areas where if you can't produce the actual component, the actual prototype with 3D printing technology, you can still use it in other areas, or you can also use it for you can use it in hybrid, what we like to call hybrid production. So often you'll find that 3D printing, in terms of dimensional accuracy, it's not as accurate as, for example, machining. And so what you can do is hybrid production, where you produce your component in 3D printed plastic, and then you machine away the specific, if there's specific areas that you need specific dimensions, you can machine those areas. So you're using the advantages of both technologies. So there are other areas that we realized that we could implement the technology within prototyping. And then if you go back to that product lifecycle graph, we also started to look at the other end of the curve. So, these are kind of the two easiest places to adopt 3D, is prototyping and then your spare parts and your digital inventory. We find that, most industries, when it comes to spare parts and procurement, that tends to be quite, and even with us as well, it tends to be quite a big pain point, because at the end of I think actually I'll go on to this on the next slide. So one of the examples within HP itself was the example of spare parts. So, you know, we found a great opportunity within our large format printing business. So these large presses for us can have a lifespan of well over 10 years, and often well past the point at which production of those models has ceased. So we still need to be able to service them somehow, so people can continue to use them. At a certain point within our product life cycle, we do a final buy where we place a final order of the quantity of parts that we think will fill the need for that particular machine for the rest of its life in the install base, whether it however many machines they are. So we place a final order, and I'm pretty sure many of you do this as well. And these are then warehoused and used when needed, and often in order to get a lower price, because the parts are injection molded, you order far more than you need and end up with 50% that usually end up not even being used. So for us, we thought that this is a great opportunity for 3D printing and maintaining a digital inventory of spare parts. So let's just print them when needed rather than having a warehouse full of them. And also those warehousing costs as well, having space, inventory, a warehouse. If you start to look at removing that or reducing that, you can find significant savings. So what we thought was, this is going to be really easy for us. We'll just replace it. But it wasn't possible because what we had was obviously our own internal processes that we had to try and get through. So what we found was that we weren't allowed to just, at the end of the product's life, start printing the parts. That process had to be validated at the start of that printer's development. So they wouldn't let us do it. So what we've now started to do is every single time we produce components, or not every time, but for specific technologies, when we produce components, we validate two processes. So we validate 3D printing, and we also validate the injection molding process, whatever it is, so that when it gets to the end of the life of that printer or whatever it is, we can then, instead of having to order loads of parts, we can produce those parts with 3D printing. And because that process was validated at the start, we shouldn't have any issues. So this was something where we had to discover that, we had to change our own processes and the way that we think and the way that we work, because we couldn't do it either. And it's a hiccup that a lot of people kind of come along. We find, our customers come along, and we understand your pain in that sense. Adopting 3D printing throughout our business was not an easy process at all. It was difficult, and not only did we have to convince kind of the higher ups that this is the right way to go, we had to implement new supply chains, but I'll come back to that. So this next video just shows you sort of some of the parts and a little bit about the person, I think, who was heading that journey.
There has been a lot of talk into using 3D for spare parts. We have several thousand of parts that are very low volume, and manufacturing them is always a problem. Finding technologies that allow us to do smaller batches of parts more adjusted to our real needs was improvement in our supply chain. I had these parts and other parts that we were planning on my desk. Many R&D engineers were going through. All of them were stopping by, and they were excited. Oh, this could be done. If these are small covers from an existing printer. This is a printer that has been manufactured for more than 10 years, which means that it's difficult to get them from the original technology, from injection molding. What we learned is that it could be easily used for many other parts. We are going now to bigger challenges for the next generation of.
So you can see some of the parts in that video. So the next kind of stage that we looked at is manufacturing tools, jigs and fixtures, things that can support and support your production cycle. So, at the bottom, these are not actually parts that are within the process or within the numbers, they're aids. And so, we've placed them at the bottom. But this is kind of the next kind of area that we thought was the natural next step for us to go to. So one of the examples that we've got from here, and like I mentioned to you, there was a site we don't manufacture our own parts, you know, we use third parties. And one of our sites, I think they're in Malaysia, this is the site that's actually produced, bought a machine because they found so much advantage from 3D printing. I can't remember, I think in their first year they had about 80k worth of savings just from replacing injection molded or machined jigs and fixtures to 3D printed ones. So the example here is I don't know if you've seen the sprocket printer that HP has. It's like a handheld. I'd call it like the modern day Polaroid. It's like a handheld device that prints photographs from your phone. This is the manufacturing line that produces the paper for the sprocket printer. And on the right, you can see that they set up a manufacturing line in order to be able to address 2 different sizes of media. So for the larger printer and for the smaller printer. And originally, it was only able to do the smaller paper. Then we decided to release a new product, and they needed to be able to find a way to switch between the smaller paper and the larger paper. So initially, they did an injection molded part. It was quite costly. It was quite bulky. It was difficult to get hold of. It took them 13 weeks to get hold of it. There was quite a long changeover time. I think it used to take them a couple of hours to switch over between the smaller one to the larger one. So what we did with them was find them a solution that reduced the changeover time from a couple of hours to I think about 45 minutes. It reduced the lead time for these parts from 13 weeks to 2 weeks, and that is significant for us because these lines change quarterly, and so 13 weeks, you know, is a good couple of months. And so, you know, you can very quickly switch between parts rather than having to wait 3 to 4 months for your components to arrive. And the tooling cost significantly reduced as well. This was like an incredible example for us, and it was all to do with just, you know, being able to change that exact same part between that part that's there on the right hand side, that fixture, sorry. All they literally do is input like another little slot in there to allow it to be able to take the smaller paper or the larger paper. So really great example for us. And then the other one is that drill extraction shoe that I mentioned earlier, and the fact that it just went from being so many parts to a single part. It's got ease of being able to be cleaned, and significant weight reduction as well, because these drill extraction shoes are not in the easiest locations to access, and so for the engineers to be able to get to those areas and clean them out, or have to change them, having a very heavy one before was not great. So it's you know, had great advantages for us, and this is actually a totally different location to the one that was on the previous slide. So we are adopting it in lots of different manufacturing sites across HP. So we then found a great opportunity for 3D printing as a tool for bridge production. So getting to market quicker and to learn and test on demand. So here you can use the mold examples that I mentioned from earlier, or when you're introducing new products. If you don't know how the market's going to receive them or adopt them, and you want to produce a small number, you can use the mold examples, or you can produce certain areas or certain parts of it in 3D printing. Especially if you know how high, and once you know how high the demand is going to be, you can decide whether you want to move to injection molding or not, or how it works. And again, because our material being quite strong and quite comparable to injection molding, if your final part's going to be in plastic, well, you can just produce it in a material that's very close to it in function, which is our material, to give you a good idea of how it's going to be received and how it's going to do. So bridge production is a great place for us. And we're always releasing new products. So for us, this example that I'm going to show you now, what you see is a brand new product in a brand new market category that for us didn't exist. It's a near-mounted 2D and 3D camera, and to it goes with a sort of like our blended reality strategy, an area that we've started to work on. So since the product category was new, the priority was on learning and speed. It also meant that we had very little way to estimate the demand, so the production volumes were uncertain. The part that you see in the bottom right, which I'm about to show you now, is still in production today, being 3D printed, this bit over here, which is a 3-in-1, actually no, sorry, not this one. This one over here, this thermal duct over here is still in production with 3D printing today. And this 3-in-1 foot was initially done with 3D printing, but because there was 3 parts to it, eventually it made more sense to move this one over to 3D print injection molding. But the design had to be changed because the current 3D printed design was unable to be injection molded. So we had to have a few design improvements, but once we knew how the market was receiving it, we were able to figure out economically what made more sense. And because there was only a single one of this duct for each of the 3D cameras, or scanners, should I say, this made sense to just carry on being 3D printed. And for us, it gave us an idea of, how the market was going to receive it. It reduced our lead time. Instead of having to get a tool created to injection mold this and this, and having to wait, up to a good couple of months for that tool to come back, we could just produce them, 3D print them, have them within a couple of days, and send them out to the market. So for us, this was great. And this cost advantage over here with this thermal duct, if we injection molded it, it would have cost us about 50k more than it did in the final part now as just being 3D printed. So it had a good advantage, a good cost saving for us as well. Just a little video. Normally I play my videos, but this one automatically started. So that was just like a little video just to show you the actual product itself. Okay, so those areas were quite easy areas to adopt 3D printing, and majority of companies, if not already, they probably are doing this, and is, if not, the easy place for you to start looking at 3D printing. But for us, that's a very, very small amount of actually where the full production happens, and the volume of parts that are produced in those stages is very little. So for us, it's not like, in terms of what we wanted to do and try and hit that manufacturing industry, we're not actually hitting that. So we needed to try and find places where we could introduce 3D printing into full production. And so we found an example, though the example was a bit of a cheat example because it was a manufactured part, but it was only a quantity of one, which was this printer that we needed for the International Space Station. So we were approached by NASA to produce a printer, because the way that printers work is that they work with gravity, so your paper drops into your tray. So what they needed was a printer that was able to catch that paper, so that the paper doesn't kind of obviously float away, kind of thing. So they approached us and they said, look, we need a printer that's going to work in space. This is just a standard 2D desktop printer, and what we did was develop this. The printer itself was a standard printer, but we developed this feeder, paper feeder and catcher, and you'll be able to see it in the next slide, I think. Yes, here it is. So you can see here that the printer itself, like I said, is a standard. It's this bit over here, which was developed purely for them. And so yes, it was a manufacturing part of quantity one. So this was kind of our first full production part. And the part itself was actually made in a material that wasn't even available at that point, because it had to be a material that could handle slightly higher heat resistance. We kind of expedited our development process for our PA12 glass bead material, and enabled it to be used. So we have a printer that's floating around in space at the moment. But this next video kind of just shows you a bit of the development process.
Our mission in HP is to engineer experiences that amaze. And there is not a better example of that than the work we have done with NASA. In space, there is no gravity, and our printers work today because of gravity. The only way we were able to address this problem on time was because we had access to HP 3D printing technology. We were able to design more complex parts, but that are also much simpler and more flexible. But at some point, we also had to test the whole printer in a zero gravity environment. And this shows both how capable our teams are, but really that anything is possible when we work all together.
So that's a nice little case study, but obviously not a truly proper production part. So I'd say our first real case study of where we actually used 3D printing in manufacturing is this next part, or this next printer. So this is our latex printing business, and there are several machined components within the machine, and one of them is aluminium. And we decided to, I think our engineers actually brought it to us and said, look, do you think you can do anything with this in 3D printing? It was quite a large, a heavy aluminium machined block, basically. It was 355 grams in total. And we had, obviously, we produced loads of these machines. And it wasn't very complex, as you can see. And so the first thing that we did was just change it into like a 3D print block design, as you can see here. We just cut off like the big chunk of material, pointless material that was over here. Obviously, in machining, the more moves that a machine makes and the more complex a part is, the more expensive it becomes. So, you know, we'd clearly probably left that bit there just because of the cost it would have added to the part itself. But in terms of weight savings, just changing it to plastic and cutting off that chunk that was there, it reduced it to 80 grams, so significantly reduced the weight of it. What we then did was, because with 3D printing, you can have a bit of complexity to your design. You don't have to have things that are block and squares and solid. We put a lattice through it. Now, we were walking around, this reduced the weight to 55 grams. So we were walking around with this design for a good year, showing everybody how amazing it was going from this block to this block over here. But really, we hadn't done any real 3D design. You know, all we'd done was stick a lattice through it, and it still performed because, you know, like I said, it wasn't a very complex part. But we hadn't really used 3D to its advantage and for the function of what it's for. So what we then decided to do was run it through topology optimization software, which adds mass just to sort of the location where it's needed. You put in your constraints. If you haven't used topology optimization software, you put in your constraints, you put in your space, you put in the stresses that are on the part, and the software itself produces you a part to a minimal mass. This was kind of the design that we came up with. And as you can see, it's a bit organic. It doesn't look like a traditional designed piece. What you'll find with most designs and designers is that we're used to looking at symmetry, and so everything that we create, we try to create it symmetrical. When you start using topology optimization, you get very organic looking structures and nothing looks symmetrical anymore. It looks very futuristic and looks a bit alien. But, you know, it gives you a part that actually does what it needs to do. And so that further reduced the weight to 23 grams. And, you know, we just made sure that we kept some of the edges, like we don't need all these flat faces, but we just kept them just so that, you know, it fits into the current space like it needs to properly. And this still does what it needed to do. Now, this part, though it's not a very complex part, the job that it does is quite complex. So it's part of, it's part of something called a spectrophotometer, which actually measures the correct color. So when you're looking for a HB blue or a Coca-Cola red, this is part of that carriage that helps carry that spectrophotometer. And so it is quite a critical part within our machines. But it didn't really have very much weight on it, which was an advantage. And so what we found was, just by going from the original design to the final design, we had a 93% weight reduction and a 50% cost reduction. So significant improvements. And this was our first proper manufactured part. And so this is now no longer CNC machined, it is produced within HP printers. But we wanted to push the boundary a little bit more. And so for us, a next natural place to look for MJF technology was the machine itself. So, you know, the quantities of the machines that we're producing is thankfully, you know, we're in a lucky space where we're not producing hundreds of thousands of machines, we're producing more in the tens of thousands. And so where you've got that break-even point for when it comes to injection molding, we weren't quite hitting it. So injection molding can be quite costly for us. So having to look to replace injection molded parts with 3D printed parts made sense. So for the larger printer, this one over here, half of the plastic parts within the printer were printed by the printer itself or the technology itself. So, you know, many parts within this machine. And again, we're not producing them ourselves, it is our suppliers that are producing them. And I think the break-even points for these parts, just by sort of redesign or thinking about combining different parts, single parts into one, climbed from sort of 5,000 parts up to 40,000 parts, just as we started to understanding how to learn, designing for additive. So that was like another great case study for us. But the next one is where we really made a real difference. And the only way we actually were able to make this real difference was by actually getting our engineers to go on training courses, understand how to design for additive manufacturing, how to understand where to apply lattices, how to produce lattices, how to use topology optimization, how to use generative design. We had to show them, you know, the real capabilities of 3D printing and what softwares can do now, to get them to properly adopt the technology for the production of the 500, 300 series printers. So in these printers, initially, it's a small printer. Again, quantities are in the tens of thousands. And when we first initially started to design it, our designers themselves were quite skeptical about 3D printing. You know, again, being very used to it being a prototyping or a little toy technology, they weren't sure if they weren't sure if 3D printing could meet the needs of the parts that they needed to do, and be as robust enough. So they came back to us with 29 parts that they thought could be 3D printed from this machine. And you know, for us that wasn't a good enough story to tell, of course. And as well as that, we thought we could definitely do better. So that's when we provided them with the training, sent them back, and those 29 parts quickly turned into 100 and over 140 parts. So within the printer there are, and this is 140 unique parts. Some of them are multiples. So in total, I think there is about 250 parts within the printer at Sunderland that are actually 3D printed themselves. But it's sort of individually unique designed parts. There's more than 140. So looking at some of those parts, and we'll go more into this in the final stage of my presentation today, is these sorts of designs. And as you can see, a lot of them, especially like these ones over here, are not your standard designs that you'd normally see. Especially if you were designing for injection molding or machining. Some of them quite complex looking. Many of them have more than one function. Many of them are multiple parts that would have usually been injection molded in 3, 4, 5 parts, are now 3D printed as a single part. So this is just sort of some of the 140 parts. But yeah, like I said, we'll go into some of the more funny looking ones afterwards. One of the examples is this 3D printing, this 3D printed duct. So our parts are fluid tight and airtight, and this actual duct was never designed to be injection molded. If it was designed to be injection molded, it would have involved about 6 different parts, as well as like a threaded insert, and it would have been quite costly to produce. It was always designed for 3D printing from the get-go. So as you can see on the right-hand side, it is one single duct, and then it's got another attachment to it at the bottom afterwards. But that key area over there is one single duct with a fan inside of it. And for us to produce it with 3D printing, it had a capital expense avoidance, or we avoided a cost of 190K in tooling. And then when it came to production costs in total, that amounts to a total cost saving of 30% in comparison to if it had been injection molded. So for us, this was quite a good example. There was also time savings for the designer as well. Now, we have a partnership with Siemens, and Siemens were looking for, components that they could really truly show their value on. And we were in a meeting with them, and whilst they were there, they saw this duct and they said, you know what, we think we can design this better than you guys have done it using our software. We're going to show you what our software can truly do. So they analyzed the duct, and they using CFD were able to see that, as the air is sucked out. Oh, what I forgot to explain is what the duct itself actually does. So this duct helps to keep our print heads cool within our printers. Now, the print heads are susceptible to heat and dust, so they're working in very, very difficult environment for themselves. So what we need to try and do is keep them as cool as possible and extract that heat. So this is what this duct does. It's attached to the print head carriage and it extracts the heat. And as it does that, you can see over here, oh, I paused it too late. Let's go back to that. As it does that, you can see that there's a lot of, pause, there we go. So there's a lot of turbulence at the start over here. The flow seems to be okay towards the end over here, but there's a lot of turbulence over here and on the corners and the edges. And so they said that, we feel we can improve this part for you. And they did. They changed the design from being this sort of single 3D printed part to this single 3D printed part, which, as you can see, looks quite organic. And different to what you're used to seeing. And over here, you can't see it properly, but there is basically like a tongue in the design. And again, a tongue is very organic, but it's in terms of its design, it helps to improve the flow of the heat that's extracted from the print head. Now, I'm not going to go into it too much because the video itself explains it, and it explains the full Siemens process and what the technologies, the software, is capable of doing, all the way to the end in terms of being able to produce a digital twin and sort of your smart factory environment. But they go through the story a lot better.
Additive manufacturing works always from the application backwards, user-centric. If we're not helping customers visualize the potential of this new technology, it won't happen naturally. We came together with the new development from HP for the much more productive 5200 series system, and the Siemens software solution. A deadline is the mother of innovation. This started a few months before we launched the 5200, and that gave us a couple of months to come up with something.
So we got our teams together for a workshop in Vancouver, Washington, and we spent 3 days together, locked in a room. We talked about structures in an automobile that you could optimize for crash protection. We talked about cooling in batteries. All that while we were brainstorming, there was this unassuming cooling duct sitting in the middle of the table. Finally, one of our guys picked it up and said, "What is this?"
Of all the possibilities, we landed on a duct, which is part of our own HP 3D printing devices.
To maintain the reliability for that print head, we need to keep the ink cool, and that's done through the cooling system. The duct was an integral part of connecting the fans to the cooling of the pen. We already had a 3D printed version which combined 6 parts into one, but we wanted more. We wanted more performance from the general flow, and we wanted more balance between the two print heads.
Our optimization will look at which parts of that design space help to gain our engineering objective, which is minimizing pressure loss, and basically then remove those parts which are detractors. We had a super large amount of recirculation, so basically the air is going in circles, losing a lot of energy. Now we have basically 4 distinct flow guiding veins which take out the swirl and immediately force the flow to go straight forward instead of going in circles.
So it was really hard to wrap your head around that geometry when we first got it from Julian, just because it was so different than what everybody was expecting. So I had to take that geometry, smooth it out, create a thin-walled part from that we could use to create the duct part. I mean, when you talk about how the original duct was designed, where a person had to manually make every radii, every extrude, every little feature on that part, with a simulation-driven part, you don't have that. The simulation makes the geometry for you, and that is a much faster process than trying to design all that by hand.
As the design was shaping up, and it defied whatever everyone, including me, was expecting it should look like, with the tongue sticking out.
I was pretty stunned when I learned that the software predicted a 22% improvement in airflow.
22%? That seems pretty high compared to our baseline. But again, Siemens, they are the simulation experts. We had to go back to the physical world and actually test that new design is going to deliver more airflow.
Sure enough, when we went back and measured, the Siemens design duct improved the airflow by 22%, just as the software predicted.
On the other side, normally you need months to develop these, and here we have reduced the innovation cycle time by 75%, which is quite remarkable to think about, because it's not like you landed on a design, you landed on the most optimal design for that particular problem.
Getting the optimized design was just half of the battle. The next part of the challenge was transitioning that design into the AM factor where we could produce it at scale.
A lot of companies only have experience with lab-like environments. So they have 2 or 3 printers, they know how to operate it, but they actually don't know how it will look like if they ramp it up with more printers. We are able to show the full simulation up to 100, 200, 300,000 parts by utilizing a digital twin, and then start with different scenarios to optimize how to improve it. For the end state, with 300,000 parts, we would need 36 printers and 6 workers. We can take an application with improved performance from the flow optimization, show that we can produce it in the industrial printing system, and this is unique in the world.
It kind of tips engineering on its head a little bit. Engineers no more should really be focused on the form and what the product looks like. They should be focused on what the product needs to achieve.
We've got a part now that has done something that I don't think anybody else in the industry has done. And when you combine that with HP's ability to industrialize additive manufacturing with their printers, it's a really strong solution.
Interest in this type of solution has been outstanding, and not only in the automotive industry, but also consumer goods. Think about refrigerators, air conditionings, vacuum cleaners.
What I'm most fond of from this project is going into meetings and handing the duct to a CXO and having them hold it and be inspired by what was possible with additive manufacturing and generative engineering, and wanting to be able to find a way for their company to be able to repeat this kind of success.
So that's a really brilliant example, just to show you what 3D printing really can do, what it can fully achieve if you are utilizing it the way it's supposed to be utilized. So, you know, the key takeaways from that was that for us, it increased our print head speed by 14.8%, which meant that our printer could go much faster. And that was all to do with this brand new design, which could only have been produced with software. As much as, you know, designers are able to produce brilliant designs, the time that it takes, it's incredibly time consuming, should I say. And so using software can significantly reduce that development speed, that development cycle, and then produce, like they said, the most optimum design, the one that will work the best in that situation. And it's an internal part, so it doesn't need to look, you know, amazing. Though to me, it looks very futuristic, and it does look quite cool. But yeah, it's not what you would normally class as a good looking part, let's say. So again, in this case, it doesn't matter because it's a part that just needs to function properly. And like they mentioned, what 3D printing can do is reduce that development cycle. So, you know, where you've got your traditional path, you would design your part, you would design it for manufacture, you would process the simulation, you would design the tool, you'd get the tool created, you would build it, test it, and if there was something wrong, you'd have to start again, get that tool redesigned, etc. You know, the process is quite long. With 3D printing, you can design your part, design it for manufacture, build it, test it, and bring it back again. And actually, what you can do usually in the 3D print with 3D print as well, you can build multiple of them in a single build, and so you can have multiple different designs and iterations very quickly, you know, within like a 24-hour period, in comparison to this process, which is quite long-winded and quite difficult. So sort of the three takeaways, the three key learnings that we had from this was, it was all about changing our mindset. It was changing the way that we innovate and do business. And you know, we found that one of our challenges was changing to get management all across different levels of the organization to truly believe in this and think that it was the right thing to do, because without that we wouldn't have been able to enable the supply chain, enable the processes the way that we did. You know, we needed to rally teams across functions to think differently, and transfer knowledge across, you know, to everyone, and especially, like I said, 3D print knowledge as well, how to design for actual additive manufacturing. And now within HP, we've got more than 10 business units that are engaged and using 3D printing, whether it's for, you know, different stages of the PLC. Majority of them are using it for manufacturing, but we've got so many different units engaged now, and we're only just getting started, kind of thing. And then, you know, one of our sort of key learnings was actually having to enable that supply chain and having to work hand in hand with them. You know, we're not just going to give you this technology and sort of set you off on your way. You know, supporting them, helping them, making them understand how to use it, the advantages of it. And so many of our suppliers now have got our technology and are producing our parts on our own technology, which is just, you know, is brilliant for us. So this next the next couple of slides is I guess an analogy to try to explain that the process for 3D printing for a lot of companies and for ourselves as well. The way that we like to kind of describe it is like a mountain climb. And you know, if you're climbing to the top of a high mountain, you have different camps that you have to kind of reach. And so the first camp in our mountain, let's you know, in our 3D print mountain, for us is, which is kind of the basic that most people enter at when it comes to adopting 3D printing, is the technology replacement camp. So camp 1 is where you are literally looking at a part and replacing it kind of like for like-ish. So the way that you could look at that is the that little bracket that I showed you that was in the latex printer, was having the metal part, and imagine replacing it with a 3D printed chunk of plastic. Now, in that case, that would not have been a viable solution, and that chunk of plastic probably would have worked out just as expensive as the machined block. And so, you know, it's very rare that technology replacement will give you a good value prop for 3D printing. It might do. There might be the odd few cases where it does, but majority of the time, just replacing a part that's produced in injection molding or a different process with a 3D printed version is not going to give you that many advantages. But that is the easiest way for somebody to adopt 3D printing. The next camp, or camp 2 for us, is performance improvement. So this is where we start to look to simplify designs, improve the performance and lower costs by using 3D printing to combine multiple parts and functions into a single piece. So at HP, we're identifying a number of opportunities in this camp. And, you know, we did look at a few, for example, that if I look back at that bracket, going from the original metal part to the final topology optimized bracket that was on the right hand side, was a performance improvement. So, you know, it still had the original design. It wasn't designed from scratch for 3D printing. 3D printing was kind of the end solution, but it had a performance improvement by weight and cost saving. And then the kind of final area, or the final camp for you, is your summit camp. And this is where you're truly using additive design. You're changing the way that you think and the way that you do things. You are looking to design for function, for performance. You're not looking to design for design something that's already existing in that sense. And if you really adopt 3D printing at this stage, and this is definitely the most difficult stage to adopt it at, you'll really see changes, and you'll really see the advantages of 3D printing. So for most people, I usually say just skip camp 1 altogether and go straight to camp 2. Look at the advantages that 3D printing can bring to that particular component, whether it is a weight saving, a cost saving, a size, whatever it is. Start to look at performance improvement, combining multiple parts into a single part. And just avoid just trying to do a replica of it with a 3D printed one. The next couple of slides are just a couple of videos of our own HP engineers who have designed, I think most of them are part of the team that have designed the color printer, or the white or color printer, and just their takeaway after utilizing 3D printing, because again, just like everybody else previously, they didn't use very much 3D printing.
One of our major design challenges was designing a part that provided the functionality that we wanted, and MultiJet Fusion allowed us to achieve that in a very short amount of time. We cut down our tooling lead time from 7 weeks to a matter of days, and it came down to the question of what are the limits of this technology and how can we push those. So we needed to feel confident that MultiJet Fusion technology would produce the parts that we wanted, as compared to traditional 3D printing methods. Being able to see and feel and look at your parts is such an important learning process, and that's what helps us move on to our next iteration, and that allows us to design closer to our solution. That's really what gives the edge and the hype to MultiJet Fusion.
One of the biggest challenges is rethinking the approach to product design. What HP MultiJet Fusion does is basically place the manufacturing tool set in the heart of the R&D development process, merging two critical elements of the development process together. I would say to an engineer who is not using MultiJet Fusion that they are overlooking a critical tool set that enables them to innovate, learn much quicker, and focus their time and energy on delivering a part design that delivers customer appreciated value. It's transformational.
In the past, whenever you do your design work, you need to follow the certain rules, how it makeable, how it moldable, how it manufacturable. But once I use MultiJet Fusion, all that kind of a constraint going to disappear. In generally, my design cycle is about 50% I can reduce, because you can just focus your design in the 3D CAD, and then you can print out, as you can see in the CAD. MultiJet Fusion going to provide us freedom of your design and the flexibility of your design. The other 3D printing technology, they don't have enough resolution to make my parts. The strength and resolution, those two are the most benefit. When I introduced this example to our team, they were also very excited. I believe that this is just the beginning of the new era of the design.
So hopefully you got the sort of the key learning outcomes that I was hoping from that area, or from this section, should I say, and hopefully it started to give you some ideas of where to look for opportunities within your own business. The final section that I wanted to focus on today was something that we like to call new design paradigms, and it starts to look at sort of understanding costings with our technology, and probably similar technologies when it comes to sort of powder bed fusion, because again, 3D printing, you've got the way that you produce your parts is effectively the space that you've got available and how you utilize that space. So Hopefully you'll understand how to take advantage of design freedom without design ignorance, explore new design paradigms enabled by additive manufacturing in both existing and new products, and then finally learn how to optimize design for the MultiJet fusion process. So the importance of materials within 3D printing, I'll start by taking you through the importance of selecting the right material. So 3D printing itself, when you have your final component, the bulk of the cost of that part, so that image over there on the left hand side of this little it's a little keychain, that is probably, it's quite small, it'll fit within the palm of your hand easily. So that, when it's 3D printed, will probably cost about 80 pence to produce. Whereas, as you know, if you produced a keyring with injection molding, you can probably get the cost down to like a pence, like a fraction of the cost. Maybe not this design, because this design has got a moving part within it. But a simple keyring, let's say, you can make it a lot cheaper. So for us, what you'll find is that the keyring, the material, is the bulk of the cost. So the material is makes up 68% of it, and hardware depreciation. So the cost of the machine is actually quite small in comparison, and the operation of the machine is a little bit more. But the bulk of the cost is the material, and that's why it's so important to properly understand how to I guess design for 3D printing so you can reduce your material cost. So just like every other kinds of technologies, every technology has got its advantages and disadvantages, and we're not saying that MultiJet fusion should be used for everything. It's got its pros and cons. So if you look at machining, it's great for good dimensional accuracy and material versatility. You can pretty much machine anything. I'd say it's actually better than good dimensional accuracy. It's probably the best in all of the processes. The disadvantages are that you are limited by the geometries that you can produce. There is a lot of material wastage because it is subtractive technology. So you're starting off with a block and then removing material from it. And part complexity is very strongly linked with higher costs, because then you'll have more machine operations to do. With injection molding, you've got advantages and disadvantages again. So, the advantages are that you have good dimensional accuracy, great repeatability. Honestly, it's probably one of the best technologies for repeatability, and for low cost for medium to high runs. And then the bane of HP's life is the surface finish that you can achieve from injection molding. Everybody is used to a smooth plastic part, and with injection molding, with HP's 3D printing technology, our surface is quite rough, and so unfortunately we can't achieve that surface finish that people often are looking for. The disadvantages are that you obviously have a high initial investment to produce the mold itself, so tooling costs. Again, you have geometry limitations because you are producing a tool, so you have to worry about things like draft angles and wall thicknesses. And then again, part complexity is linked with higher costs because then you have to produce a very complex tool. And with 3D printing, and specifically HP's 3D printing, you've got to think about the same kind of design rules. With injection molding, you're used to designing for shrinkage. With HP's MultiJet fusion, we're using thermoplastics, which again can shrink, and so you've got to start thinking about those kind of rules, as well as, like I said, how you're going to place things inside of the build itself. So the very kind of the first thing that we start to get people to start thinking about and doing things differently is, for injection molding, for ease of design, we're used to most boxes being like an orthogonal box kind of shape, a square kind of shape. Now this is brilliant for injection molding because it reduces your part cost and it produces what you need to produce. And if you were then wanted to produce a box in 3D printing, you'd probably go with your traditional mindset and produce it the same way that you normally would think that a box should look like. But for our technology, that's actually a disadvantage, because what it means is, as the way that the printer works, as you saw, we use the thermal process, and we've got an infrared sort of lamp that applies energy, heat energy, to your surface to fuse it. So you'd have, if you were to take a cross section of this box at the top, you'd see that you'd have you know, a nice sort of small area that's being fused, another small area that's being fused, and then when you reach that top bit, you've got wham, a huge fat layer of a huge flat layer that's got a lot of heat, and it's absorbing a lot of energy, which might cause it to have some kind of shrinkage or sinkage in the middle. You then have, but in order to design for 3D, it'd be better for you to think about, you know, changing the top of that box or the bottom of that box to maybe a dome-like structure, so you can reduce that thermal energy, and again, corrugation, which would do a similar kind of thing. So you have to start thinking about designing for the process itself. So what thinking like this, what it allows us to do is create extremely consistent and repeatable parts for you. It helps us hold dimensional tolerances, and parts that are free from issues that can occur, like warpage, sinkage, and others. Okay, so there are several points in the development cycle where additive manufacturing can be incorporated into the design. Ideally, it's is envisioned from the outset when a product is defined, but we know that's not always the case. Often, as designers, we have to adapt an existing design to benefit from the economic advantages of additive manufacturing. So when this happens, we need to work out whether it makes sense to redesign the part. So there are several points in the development cycle where you can do this, and the very earliest point is when additive is picked for an economic advantage. So when redesigning a part, one of the factors you need to consider is the solidness of the part. For very dense parts, the potential reduction in weight and the cost is a key advantage brought by the design freedom of 3D printing. So these parts are ideal for applying redesign strategies. Another factor is part size. So for parts with higher production volumes. So what parts should you redesign? Let's look at the part type first. If it's a solid part, for very dense parts, the potential reduction in weight and cost is a key advantage brought to you by the design freedom of 3D printing. So these parts are ideal for applying a redesign strategy. What's the next consideration, which will determine whether it makes sense to redesign a solid part? You've got part size. With large parts, if we reduce the weight by a certain percentage, this will result in lower costs and increased performance, and the resulting part will be lighter. What if it's a big part? Then yes, we should reconsider designing it. However, if the part is small, when it comes to small parts, we need to assess the impact of the change on production volume to justify the time we've spent redesigning the part. So if the production volume is high, then the impact of redesign to lower part weight, and hence the cost is significantly higher. If the production volume is low, then we need to analyze the business case and consider what is the next consideration if the part isn't solid, is the part size. So for example, is the part big? Then we need to check production volumes, and if the volume is high and redesign, so you go back around the decision tree, and if the part is small, then it really doesn't make sense to redesign that part. If the part has already been designed, then usually the simplest way for you to redesign it is to, one, hollow it, which is remove weight from it. Two, if hollowing it is not going to be able to allow it to perform its function, then you can use a lattice structure, which will allow it to still have some kind of structure inside of it. Or you can use topology optimization. Those are kind of the key things that you can do if the part has already been designed. So that was the example that I used with that bracket, and what I was explaining earlier as well. For us, that was kind of stage 2 of that camp, where we had to redesign an existing part. So we couldn't still get the full function of this part. If it'd been designed for additive right from the get-go, it probably would have looked slightly different. So when what redesign strategy should you apply? depending on the mechanical requirements, the performance complexity, the size of the part, the production volume, what should you use? So if we look back at the decision tree to determine the best redesign strategy, let's have a look. So let's start checking the mechanical properties of the part. So if the mechanical properties are important, what is the next thing that we have to check? If the performance is key for the part, what else has to be taken into account? If the production volume is high, then we can use topology optimization. If the production volume is low, then there is a business case for you to redesign the part. If performance is not an issue, then take into account whether the part is solid. If it's solid, then use a lattice structure. If the part isn't solid, then manually modify the design. If the mechanical properties aren't important and the part is solid, then simply hollow the part. That's probably the easiest thing that you can do. And there it is, sorry. And if the part isn't solid, then you need to modify the design manually. But if additive manufacturing is considered from the start, we can achieve value that can only be achieved with additive design. And so let's have a look at an example of this. So for us, one of these examples is going back to those parts that were in the 500, 300 series, is these weird, complex kind of looking like parts that were in there, which, you know, we can only design as having a bit like a skeletal kind of structure. And the reason for why, you know, we've created these is because they help us to control our thermal mass, increase that repeatability, and hold those tighter tolerances that we're talking about. Like I said, if this was injection molded, maybe you would have just a flat surface because that would be easier for you to mold. But for us to print that big fat flat surface, it will mean that we're likely to have maybe shrinkage or sinkage. And so for that reason, we would actually design it totally differently, with a totally different idea. And in this case, create kind of these kind of structures and remove material that's not needed. And so that's why these kind of look the way that they do. Looking at that on a I guess a more basic part, you know, this is kind of what our parts are going through. So say this was your original part, this kind of step with a larger step, and what could potentially happen within our machine is warpage, because you've got a load of heat in one area and then the area towards the end, which is quite cool, and so it's quite likely to warp slightly over here. So to avoid that, for us, one would be to try and have a lighter design, so to create a lattice structure through it, or to have a smoother transition, so that it's not such a shock to the part, and so it won't, you know, hopefully won't warp or experience that kind of defect. So, you know, this is just kind of like an example just to show you what would be better for us. So if we look to incorporate economics into the already optimal design, now you can start to unlock kind of even more value. This is sort of your additive design being mixed with your economic advantage. So when we started all of this, we had a vision of what 3D printing could mean for manufacturing, and we realized we weren't meeting that vision by doing things the way that they'd always been done. We had to re-envision what manufacturing meant and how to deliver the maximum amount of value. This meant changing how we assessed parts from an individual part by part basis. So we had to change the way we think about ordering parts as well. So we took a page from the automotive book and started thinking in terms of sets, leading to a term we've borrowed from the automotive industry, which is called Kanban. This is the idea that a set can contain all of the parts that you need for a product. Printing one set gives you the parts for one printer. Printing a full build, which in this case was 3 sets, gave you enough parts to make 3 printers. This method of assessment allows for organizations to connect the supply and the demand of the system, limiting inventory and improving reaction time. So we started thinking about design in terms of increasing build density. The example on the left is a strategy also called solo cupping. So you would stack cups for efficient use of space within a cupboard. It's the same thing that you do within our printers. You can stack parts to be able to use the space that would previously have been sort of wasted. Lots of parts have orthogonal walls because orthogonal walls are easy to design, but we found that for us that means that you can't then stack them. So by angling the walls by 15 degrees, now you can stack them and also significantly reduce the cost of the build. You know, for this example anyway, by 40%. And using planar symmetry as well, you can do the same thing again, allowing those parts to stack within a build more easily. So here you've got another example that you can use is hinges, where things may previously not have been folded. You can start to apply hinge strategies to be able to get a better part cost. So this example again is from the printer, and there's a few of them as you can see on the right hand side. And what we basically did was these are O-rings, and normally, yeah, I'm sure you're used to using O-rings. They're always a solid loop. You know, it's not able to be opened. So what we created was, what we found was with the original design, we were only able to fit 108 within the build because, you know, there was a whole load of wasted space inside of it. So the designer, which was the girl in the video, she redesigned it to apply some hinges to it with some seals, and so it can be flat in the build. And that meant that the number of parts in the build went from 108 to 198, and this enabled a 45% decrease in the cost per part as well. So an economics advantage, as well as eventually a design advantage, because this particular O-ring is actually in a location that's quite difficult to access within the printer. So actually, rather than trying to sort of wiggle it up, the engineer can just sort of whip it around the back and clip it in the front, which actually makes it a lot easier to use. So it ended up having a design advantage as well as a cost advantage. And same with the parts that we designed for that printer. Originally, we could fit 2 sets within our build, and as you can see, a lot of the box shape, the boxes had orthogonal sides. So what we did was change this design, and afterwards after doing a little bit of design for additive manufacture even, we were able to fit 3 sets within a build, and that also reduced our cost by 15%. So, you know, this is really how you can get that economic advantage. Now, how does this apply to your business? It can help you, you know, to widen the part selection model, where things like mechanical properties and dimensional accuracy, etc., were important. They no longer are. It's now about optimizing your designing for assembly, and so that will help then, you know, widen your funnel and help you find more opportunities within your business for a cost advantage as well as, you know, different advantages. And that's how we at HP went from 29 parts to 140 parts, you know, within this particular example. Not only were they better designed, but economically they were all cheaper as well than using injection molding or traditional manufacturing processes. And that was kind of the focus for that last bit and the end of my presentation. So thank you very much. I think I'll pass back to you, Carl, and I think if there's any questions, then I think we'll be able to go through them now.
Thanks, Maryam. That's really interesting presentation that gives sort of a fantastic sort of overview of that whole method of working with the HP MultiJet Fusion. So if anybody has any questions, they can just send that now. There isn't anything at the moment. I think you might have covered everything, Maryam. But the question I have in terms of the so our machine is the 540 that prints in the PA12. The larger sort of like the 5200 machines, like the industrial ones, they can print with a sort of a broader variety of materials. What I know there's like the PA12, there's PA11, and there's a glass bead PA12. What other materials are coming on stream, especially with the open platform that HP has for materials?
So we have also released a couple of TPU materials over the last year, and we released PP a couple of months ago, and as well as that, TPA is literally just in the process of coming out. So we've got a few elastomeric materials. There's two different TPUs. One has got slightly higher shore hardness than the other, and one is by Lubrizol and one's by BASF, and then the PP is actually also by BASF, and it's PP is the most widely used manufacturing material that there is, and so it's opened up a lot of opportunities. PP is a great material for chemical resistance and fluid tightness, so very, very good for the automotive industry. And then the TPA is, again, it's very similar to one of the other TPUs that we've got, but you know, another example of an elastomeric material that you can use.
HP just recently, or actually it's not that recently now, talked about a metal system. That's
yes.
Have you been involved with this at all, or are you staying with the?
I'm predominantly plastics. But you can, yes, we have announced a metals machine. Well, we announced it back in 2018. The machine itself was supposed to have been available this year for the wider public, but unfortunately, due to COVID, we've got a bit of a delay on the release of that machine. What I do know is that the first material that will be enabled on the machine when it comes out is grade 316 stainless steel. The process itself is going to be a binder jetting process. So what we're using is like a latex binder, and then there's a second stage to bind the actual powder together, and then there is a second stage where we then sinter the part afterwards to give you your final part.
Good, interesting. So so I know that the advantages of HP in terms of the additive in industry has sort of had a sort of huge impact. And I think I've kind of read a stat before, I think it was saying that 50% of all printed parts that have ever been printed on the HP are actually end-use parts that have gone into, which is incredible. And I do wonder whether the metal printing is going to sort of really open up metal additive in the same way for industry, just with its, you know, with the speed that the HP system looks like it's going to offer over it's like SLM machines or metal deposition type machines with that. Well, Maryam, I can't see there's no other questions coming through, so I think we could take it that everybody must be satisfied with this.
Great.
There's a lot covered there, so people can. There's a couple of handouts which Maryam's very generously shared the PDF of her slides. So if there's anything you want to kind of like dive back into and have a look in sort of greater detail there. The contact details for the SAM project are on the screen now. So if there's if you're based in the Northeast LEP region, so that's like Durham, Northumberland, Tyne and Wear, and you have a manufacturing project that you think we might be able to help with, I mean, that's, as Roger said right at the start, it's not just additive, there's a number of different areas that we could support in. My area of interest is additive, and as well as like border design things, so please get in touch. We could see how we could help out. Roger, do you have anything you wish to add?
No, I think you've covered there really. As I say, if you're an SME manufacturer in the Northeast, then please get in touch. We're more than happy to help you. Likewise, any other manufacturers that are more locally, if they want to come in and see the technology, they're more than welcome. Such a time as we can have people in the building. It's a little bit difficult at the minute under the restrictions with COVID, but we can do remote sessions, and we can do Teams meetings, and we can do a little bit of restricted on-site meeting by prior arrangement. So by all means, get in touch, and more than happy to to help out. As I say, the handouts are there, telling you a little bit more about the SAM project. Also, take a look at the SAM website, where you'll find some more information there as well. So really, I think that's all I'd like to say for today, Carl.
Yeah,
Thank everybody.
thanks.
It was a really interesting presentation from Maryam, as always, because seen him present before and was really good. Yeah, hopefully there's a lot of detail there which covered a lot and answered most people's questions very thoroughly. I think, are we doing another? We did discuss doing some more specific sessions as well if people wanted to do a walkthrough of parts, didn't we, Carl, with Maryam?
Yeah, well, I think because originally this was going to be a live event, and one of the things that we talked about for that we could, if people had a part which they thought could be switched over to kind of producing with the HP system, then we could have a session, kind of a one-on-one session with kind of Maryam and that kind of person, and we could run through that and then use the SAM equipment for producing kind of sample parts and things with it. And that would all be funded. So
that offers there for any of the SMEs that are eligible for the Northeast in the Northeast LEP area for the SAM project, and we'd be more than happy to help with that on that path.
Yeah, I think as well as something that we did that was an interesting project using the HP system was for work holding, for a part that was going to be a large metal part that was going to be CNC machined, and because of the geometry of the part, the work holding was going to be either expensive to make or just not really feasible for the project. So we were able to kind of pretty quickly kind of design that part, print it, and I think kind of within a few days they had that kind of part ready to kind of be running in their machine shop. So I don't think just in terms of end use parts or sort of products, or there's checking fixtures or checking jigs or kind of or fixturing for other processes are kind of a massive growth area for additive. So if there's something you think in your production line that you might be able to sort of, swap out an end effector or a jig for, then please get in touch.
Yeah, I mean, obviously we're using it a lot internally for fixtures, locations, aids, and especially some of the robotics and cobotics applications for actuator and end of arm parts, where it's considerably lighter, therefore making the robot more efficient. So yeah, there's lots of applications, not just in end use parts.
Okay, right. Well, I think we can tie things up there. So thanks very much for attending. You'll be getting this session's being recorded, so you'll be getting a link to where you can view that video sent to your email that you use to kind of register. Okay. Thanks, Maryam. Thanks very much.
No problem.
Really
thank you for having me.
Okay. Thanks, Sam.
Thanks, you.
Bye, everybody. Have a good day.
Thanks.